We have been discussing two-dimensional correlation experiments. This was the cozy experiment, was the first experiment to be developed, and that was the most fundamental of all of these correlation experiments. Let us do a quick recap of what we did in the last class. This is the pulse sequence of the cozy experiment, which is very simple, consists of two pulses 90x and then the T1 period, then 90x, then the T2 period. So, T1 is one independent time variable which is systematically incremented from one experiment to another experiment, and T2 is a day time period which is the acquisition period where you actually collect the data. Two-dimensional Fourier transformation of such a data results in a spectrum which looks like this. So, we have this peaks along the diagonal which are called as the diagonal peaks. You have one frequency axis, this is called the F2 axis, or this is the F1 axis, and on the diagonal F1 is equal to F2. So, therefore, it is called the diagonal, and we have cross peaks here arising between two spins which are J coupled. So, this is the extremely useful part of the cozy experiment. So, it displays correlations between J coupled spins. So, if we have a molecule which has such a kind of a network that this spin is coupled to this spin, then it will produce a cross peak here, and this spin is coupled to this spin, it will produce a cross peak here, and this will appear symmetrically. And if there are singlets, that means which they are not coupled to anybody, they lie as singlets here on the diagonal. Notice here that this period which is given as a small gap here, this gap is really 0, it is not really a gap. This has been given here in this figure simply to accommodate this number 4, which is the time point we have indicated here, these various time points 1, 2, 3, 4, for the purpose of evaluation of the product operators at different time points through the pulse sequence. So, it is just for that purpose, otherwise this gap is actually 0. It is just minimum required to see that there are no effects of the transmitter on the receiver directly. Okay, here the transpirator is put off and the receiver is on. There should be no direct interference between the transmitter and the receiver, only that much gap is given, which is of the order of few microseconds sometimes. Okay. So, therefore, this is not really a long time gap, and started looking at the theory of this, how these diagonal peaks arise, how the cross peaks arise, what are their structures, and that is we did part of that in the last class. So, we calculated the density operator at different time points, and then we arrived at this point 4, and that density operator is called as rho 4. It had two parts, one was non-observable, other one was an observable part. Non-observable part we have just ignored here, and only the observable part is written here. Observable non-arises because of what? Because the trace of the IKX or the IKY operators, this has to be non-zero with the density operator. If you measure the X magnetization, you take the IKX operator. If you take the Y magnetization, you take the IKY operator. So, each way. So, this was the calculation which was arrived at starting from the K spin magnetization to begin with. Similar things will appear when you start from the L magnetization also, but it is enough to demonstrate taking the K spin alone. So, therefore, and we calculated the density operator at point 4, and that is rho 4. It has two terms here. So, it has Ikx cosine pi jkl t1 minus 2 Ikz ILy sin pi jkl t1 and sin omega k t1. So, this is the X magnetization of the K spin, and you see here is the Y magnetization of the L spin, which is antiphase with respect to K, whereas here it is the in phase magnetization of the K spin, and this is the antiphase magnetization of the L spin, and this is responsible for the cross peak, because in the evolution period, the T1 period, the K spin was evolving with its characteristic frequency omega k, and that appears as sin omega k T1 here, and eventually this during the T2 period this will evolve with the frequency of L and this will evolve with the frequency of K. Therefore, this one will produce the diagonal peak in the end and this term will produce the cross peak in the end. And we started actually calculating the evolution in T2 taking the first term which will produce the diagonal peak. So, what is the fine structure in the diagonal peak? Does it have a fine structure? So, we started calculating that. So, if I were to represent the part of the density operator which belongs to the diagonal peak, so I call it as rho 5 d prime, and this is during the acquisition period, and that one comes as a result of evolution of this part of the density operator here. So, this is Ikx cosine pi jkl T2 plus 2 Iky Ilz sin pi jkl T2 cosine omega k T2, and then we have Iky cosine pi jkl T2 minus 2 Ikx Ilz sin pi jkl T2 sin omega k T2. This comes as a result of evolution of the Ikx operator first under the influence of the chemical shift Hamiltonian. So, that gives you the cosine omega k and sin omega k here, and then under the influence of the coupling Hamiltonian that gives the terms which are in the interior brackets here. So, Ikx term will give you these terms, Iky term gives you these terms as a result of coupling evolution during the period T2. And this is the one which is present here, the T1 evolution contribution. FDT1 is cosine pi jkl T1 sin omega k T1, that is this here cosine pi jkl T1 and sin omega k T1. Okay. So, now if you look at this in a little bit more detail, if you assume you can choose one of these to say okay we are going to get record Y magnetization or the X magnetization. So, you can choose one of those if for demonstrating the principles. Okay. Now, if you see either case, if I take this, so I have here cosine cosine and here I have take those and this one gives me cosine sine, okay, in the T2 period, cosine cosine and this is cosine sine in the KYLZ. Okay. Now, out of these terms are not observable because this is antiphase magnetization. The antiphase magnetization is not observable, therefore, what we will restrict it to only this or this. Okay. So, assuming that we record the Y magnetization, then we will only have this particular term Iky cosine pi jkl T2 sin omega k T2 into FDT1, and FDT1 is cosine pi jkl T1 sin omega k T1. So, now if you expand this further as separate frequencies, what this gives you omega k and pi jkl cosine pi jkl T2 sin omega k T2, this will produce you two sine terms with the frequencies at omega k plus pi jkl and another sine term with omega k minus pi jkl in T2. And similarly, in the T1 period also if you take the Fourier transformation of this one, this will produce you two frequencies omega k plus pi jkl along T1 and omega k minus pi jkl along T1, which means after Fourier transformation you will get those frequencies in your spectrum along the F1 axis. These ones you will get them along the F2 axis. So, this is represented here. So, you will get a total of 4 peaks after real Fourier transformation along the T1 and the T2 dimension leads to 4 peaks with dispersive line shapes at the following frequencies. Why did we say dispersive line shapes? Because they were sine terms. The sine terms, as we have seen before, will give you dispersive line shapes, and the frequencies that are present are nu k plus jkl by 2. Now, it is written in terms of hertz, not in terms of the radians. So, the 2 pi part has been taken out. So, it is omega k plus pi jkl is the same as 2 pi into nu k plus jkl by 2. So, the nu k is 2 pi is taken out here. So, you have here nu k plus jkl by 2 along the T1 and nu k plus jkl by 2 along the T2. So, this is a positive peak and it will have the dispersive line shape, and this one is nu k plus jkl by 2 along the T1 and nu k minus jkl by 2 along the T2, and this will be again positive and dispersive line shape. And then you will have correspondingly for the nu k minus jkl by 2 along the T1 and nu k plus jkl by 2 along the T2, positive dispersive, and finally nu k minus jkl by 2 and nu k minus jkl by 2, which is also positive and has the dispersive line shape. So, you get 4 peaks along the diagonal, and we said this will produce peaks like this, and these are the 4 peaks which are present originating from the K spin as we started calculation from the K spin. Similarly, we will also get 4 peaks from the L spin if you started calculation from the L spin magnetization to begin with. So, all of these are dispersive line shapes and all of them have the same sign. Okay. So, now we continue the discussion for the other term in the density operator, which was the second term in the rho 4 density operator, and that was 2 ikz ILY sin pi j k L T1 sin omega k T1. Okay. This was the second term in your rho 4 density operator. Now, what we do here is now we have to evolve this term in the T2 time period. So, in this case we shall evolve the J first. Under the influence of the J coupling we will evolve this operator. So, if I call this as rho 5C and I get here 2 ikz ILY cosine pi j k L T2 minus ILX sin pi j k L T2 FCT1. FCT1 is this term here, sin pi j k L T1 sin omega k T1, I represent it as FCT1. And then after this J evolution we consider the shift evolution. Okay. So, each one of these terms will evolve under the chemical shift. So, this gives me rho phi C dash, and that I write it here as 2 ikz ILY evolves now with the frequency of omega L. So, ILY cosine omega L T2 minus ILX sin omega L T2, and this cosine pi j k L T2 comes from here, and then this term is minus ILX cosine omega L T2 plus ILY sin omega L T2 sin pi j k L T2, and to the whole thing you have this FCT1. So, this is the one inside the bracket is due to the evolution under the chemical shift. Okay. Now, assuming that we measure the Y magnetization, the observable signal is given by trace of rho phi C dash ILY. Okay. So, and we get here because we are looking at the L spin magnetization in the, we are looking at the cross peak. Okay. So, this gives me sin omega L T2 sin pi j k L T2 sin omega k T1 sin pi j k L T1. Okay. So, now you break this up into its components. This one will give me sin omega k T1 pi j k L T1 will give me cosine omega k plus pi j k L T1 minus cosine omega k minus pi j k L T1, and this one will give me cosine omega L plus pi j k L T2 minus cosine omega L pi j k L T2. So, if you see there are 4 terms here, this into this, this into this, this into this, and this into this. So, because of these minus signs here, we do get combinations of positive negative peaks here. So, this into this gives me cosine omega k plus pi j k L T1 into cosine omega L pi j k L T2. Okay. And this into this will give me minus cosine omega k plus pi j k L T1 into cosine omega L minus pi j k L T2. And now this into this once again with a minus sign gives me cosine omega k minus pi j k L T1 into cosine omega L pi j k L T2. Then finally this into this gives me plus cosine omega k minus pi j k L T1 and cosine omega L minus pi j k L T2. So, after 2 dimensional Fourier transformation, each one of these will produce a peak. So, therefore, where will these peaks appear? Along the F1 dimension, this will be at omega k plus pi j k L, and along the F2 dimension it will be omega L plus pi j k L. Okay. And this will have a plus sign, and this one will produce me a peak at omega k plus pi j k L and omega L minus pi j k L, and this will have a negative sign. Okay. And this term will again be negative in sign, and this will be at omega k minus pi j k L and omega L plus pi j k L along the F1 and the F2 dimensions. Finally, this will be again positive and this will appear at omega k minus pi j k L along F1 and omega L minus pi j k L along F2. So therefore, this is what is indicated here. This leads to 4 absorptive peaks at the following coordinates. Why did we say absorptive? Because you notice here all of them are cosine terms here. Since all of them are cosine terms, I get absorptive peaks. And then the signs are as indicated here. This is positive, this is negative, this is negative and this is positive, and all of them are absorptive peaks. So that is indicated here as 4 peaks. Here you can see these are the 4 peaks originating from K spin, and this is the so called cross peak. So the cross peak has absorptive line shapes in all the 4 components, and this is indicated here as minus, plus, plus, minus. Okay. This is an important feature of the COSY, and you will see therefore this is called as the differential transfer, because if you look at the total integral of this, the total sum of this, it is 0. So therefore there is no net transfer of magnetization, it is called as the differential transfer of magnetization. The coherence transfer is differential in nature, and that produces me positive and negative contributions in the cross peak. So this comes from K spin, and similarly if you start it from the L spin, again you will get 4 peaks in the cross peak here fine structure. Okay. Now here is an example, experimental example. You can see this is the molecule what we have. So this is taken from this book, Harald Gunther, NMR spectroscopy, Willis CH, and it is directly taken from there. Because this one has 2 protons, this is an example. This one has 2 protons, and therefore this is an ideal AX spin system. Okay. And if you look at the one dimensional spectrum that is indicated here, this has 2 doublets, okay, along the F2 dimension also 2 doublets, F1 dimension also 2 doublets. This is one of the spins and this is the second spin. Now you notice here this is the diagonal peak, this is the cross peak, this is the diagonal peak, and this is the cross peak. And you see here all of these have same sign and they have dispersive line shape, and these ones are absorptive line shapes and different signs. How this is indicated more explicitly by taking cross sections here. So you take the cross section at this point, that is shown here. So this comes from here, so you have a negative, positive peak, these are absorptive line shapes, okay, absorptive line shapes, antiphase in nature, we call this as antiphase in nature. So you have 2 peaks, the 2 components which are antiphase in nature, therefore you have negative and positive, and the 2 peaks which are here, you see these ones are dispersive in nature, they are in phase, they have the same sign. So you see here this goes negative, positive, this is one dispersive component, the other one is again negative, positive, again dispersive component, these both have the same sign, and therefore they go in this manner. Okay, this is the dispersive line shape. Now you take the next one here. So what was negative here now becomes positive. So negative, positive, this is positive, negative, therefore this becomes positive and this one is negative, and this goes in this positive, positive fashion once more, and then here you have the positive, negative, and positive, negative, both have the same sign. So now you come here, this is originating from the L spin. So you have now the dispersive components here. So the dispersive components are here in this manner. You have this line shape, this is going, there is 2 dispersive components in phase in nature, and the 2 peaks which are present here, they are antiphase in nature. So you have the negative, positive going up here, and this one is the next component which is present here, and that gives you dispersive component in this manner. Okay. And these are the absorptive, what was negative here now becomes positive and negatives here. This resolution is quite high. If you see here the cross peaks in all of these components, the cross peaks are very good, the intensity distribution in the 2 components, whereas in the diagonal peaks that intensity distribution is not uniform, simply because these dispersive peaks have big tails and these tails interfere with the other peak, and therefore there is a contribution of one peak to the other peak in the eventual appearance of the fine structure of the peak, and that is the contour diagram is indicated here, while these are the cross sections. Now you take the contour diagrams of the 4 peaks, this is one of the cross peaks which is here. So and therefore you have here this cross peak fine structure, this is the fine structure of the diagonal peak. Okay. So that was so much for the 2 spins. We can extend, of course all your molecules are not only 2 spins, there will be more than 2 spins and there can be 3 spins. So what happens if there is a 3 spin? So there are different situations, of course the different complexities will be there depending upon the nature of the coupling network of the spin systems. So here if I take 3 spins, I can call them as AMX. Okay. There are different ways the spins can be coupled. If the geometry of this coupling is like this, that suppose this is a linear 3 spin system, then you have the A here, M here and X here. So the A spin is coupled to the M spin is coupled to the X spin, but there is no A to X coupling. So how will the one dimensional spectrum of this look like? We have just shown it by a stick diagram. So you see, and with the different coupling constants, they can all have different coupling constants. So A spin will be a doublet because of coupling to the M spin, and that is indicated as a doublet here. Okay. And the M spin will be a doublet of a doublet because it has 2 couplings. So it has one coupling due to the A spin and the other coupling due to the X spin, that is indicated here. So this coupling is the MX coupling, and then from here to here is the AM coupling. This coupling has to be the same as this. So this is the AM coupling, this is the MX coupling. Likewise the X spin has the coupling due to the M, and this coupling appears here as JMX, and therefore we have here a doublet of the X spin. So therefore this, what sort of a cozy spectrum you expect here in a schematic? So you will have the AMX. So A will produce a peak to the M spin. So this is the AM cross peak, and the M will produce a peak to the X spin cross peak, and this is the MX cross peak, and this symmetrically appearing here, here as well as there. And all of these will have fine structures in the case of the 2 spins. Okay. Suppose we have a 3 spin which is the coupling network is like this, is the triangle. So A coupled to X, A is coupled to M and M is coupled to X as well. Therefore each one of them has 2 couplings. Therefore each one of them will be a doublet of a doublet. Okay. So there are 4 lines for each one of those, and these 4 structures of individual spins is indicated here. The A spin now has a doublet of a doublet. The one spin is the AX coupling. Here the AX coupling is assumed to be larger than the AM coupling. Therefore from here to here it is the AX, from here to here it is the AM coupling. And the M spin has the MX coupling and the AM coupling. Here the AM coupling is assumed to be larger than the MX coupling. Therefore this one is like this and this one is like this. Of course these structures can change depending upon the relative magnitudes of the coupling constants. So now the X spin likewise has a MX coupling here. Notice this coupling has to be the same what is present here. Okay. And the AX coupling of course appears here as well and appears here. Therefore this coupling has to be the same as this AX coupling here. So then you put that together. So all of these things look different in their fine structures. Now in the 2 dimensional spectrum, of course in the schematic you have here the correlations showing up here as A to M, and then you have A to X as well. Okay. And then you have from the M you have M to X and of course the M to A. So therefore you have this complete plane full, you have all the couplings displayed in the form of cross peaks. So this will enable you to identify what sort of a network of coupled spins we might have. Okay. So let me just repeat this feature once more, that for the case of 3 spins we will have the fine structure in the individual peaks. This we will discuss later, but at the moment it is sufficient to note that you have a network of coupled spins, and this network of coupled spin will be displayed in the form of cross peaks appropriately depending upon the nature of the couplings we might have. And the fine structure will be present in each of these diagonal peaks as well as in the cross peaks, and the features of this we can see in the next class. So I think we can stop here. Just to recap what we did, we looked at the fine structures of the diagonal peak and we explained how the diagonal peak has dispersive character and in phase character, and the cross peaks have absorptive character and antiphase character in the case of the 2 spins. The similar thing will happen for the 3 spin as well, and that we will see in the next class. And these fine structure calculation we did explicitly using the product operator formalism, which was extremely useful in defining what sort of a frequencies will appear, what will be the line shapes, and what will be the advantages and disadvantages of this we will see in the next class. So, I think we will stop here, we will continue in the next class.